Ready or not, here we come. Hi everybody, this is Steve coming finally to present the Machine Language Tutorial Series Part 2. Oh boy, this has been quite a journey on this one. I've been working on this thing probably over a good week, taking my books to work and just doing a lot of research, but yeah, it's finally underway. I have a couple things to go over and show you. I've learned a lot about the status register flags and been playing with those. I came across Vice and realized the Vice does not work very well in it, so I decided to go with CBM PRG Studio. Although we probably won't be doing any code yet, there's still a lot more to cover, really understanding how the flags work and just understanding some of the registers in the computers are really important too, which we'll go over. And anything else is up for grabs here. Before we do this, I wanted to kind of show you, if you have never seen the inside of one, here's a Commodore 64 board inside. And you see me talking about some of the chips. I don't know if I can do this backward or not, but this is the 65-volt chip, so this is the main brain of your computer right there. If you can kind of see, it's the processing chip there. I'll just hold it up just a little bit so you can see it. I think these might be the CIA registers. I had them replaced by a friend helped me replace some of these. And then there's the RAM chips in the front, of course. So I'm not here to give you a technical video. I just wanted to show you, basically it's sending information down on these little pins here, and it communicates directly with the CPU. That's how machine language kind of works. And it's, ironically, it's moving all across this board too, if you think about it, because it sends instructions all over the place. Now, anybody wants to give me more of a hardware, hardware perspective on that, I'd really appreciate it, because I'm no hardware guy. But I just studied those little few things, and it'd be interesting to really know what all this data bus is and how all this information communicates and translates. Wait for my monitor to come back. Okay, so we're going to go over things also like the stack today. So what I'm going to be doing real shortly here is I'll be showing you the document. This thing is already like 45 pages long and growing. Probably one of the things about me is being such a perfectionist with this. I spend a lot of time going over it and reviewing it, and just admit it's probably not perfect. There's still a lot I need to iron out. I took a lot of extracts from a lot of the different books I showed you in the first video, and I've kind of mended them together to show you different perspectives of what people, how they talked about it and how they learned in their styles and stuff like that. So let's get that started. Okay, so we left off last time talking, I think we were probably going into the CIA chip, which is one of the things I was showing you earlier, the 6526. Although when I go to look at my board, mine doesn't say 65, actually they do say 6526, okay. Mine's are R4s, whatever that means. But I had Mitch, he's one of the people I met on here, helped replace my Commodore 64 board. You saw the Commodore 64 in the background anyways, that's just a second spare board I have. So let's go over this. I'm going to read through just like before, because I'm nowhere completely knowledgeable about this, and I couldn't, recite it off the top of my head, but we'll go ahead and start reading through this again. So here's the chip, the 6520 CIA chip, and this is actually known as the Complex Interface Adapter, and it's located in memory locations DC00 through DC0F, and I put the decimal parts here, or 56320 to 56335. These handle a lot of stuff with the joystick, and we'll go over all that here. Within these registers are CIA number 1 and CIA number 2. According to map into Commodore 64, it allows the 6510 microprocessor, which we learned about, to communicate with peripheral input and output devices. The specific devices that CIA number 1 reads from and sends data to are the joystick controllers, paddle fire buttons, and the keyboard. CIA number 1 has an interrupt line which is connected to the 6510 IRQ line. These two timers are used to generate interrupts at specific intervals, such as the 1/60th of a second interrupt used for keyboard scanning, or the more complexly timed interrupts that drive the tape read and write routines. Other features include communication with outside devices such as the keyboard. And if you want to learn more about those, you can look them up in map into Commodore 64. Okay, so locations DC04 through DC07, 56324 to 56327 manage 4 timer registers. These registers hold a 16-bit number from 0 to 65535 in normal low byte, high byte format. Once the timer is activated, it begins the countdown. When timer A or B gets to 0, it will set bit 0 or 1 in interrupt control register at DC0D, decimal 56333. If the timer interrupt is enabled, an IRQ, which is our interrupt, will be set to 1. This is useful information to know, especially when you start learning about raster interrupts. Now, as I mentioned before, I'm also putting down the definitions for people who might be interested in learning a little bit more. And they're kind of tips, I guess you could say. 6510 microprocessor, according to Peaks and Pokes for the Commodore. If you've ever seen an integrated circuit, you'll know that the chip appears to have legs. Those are the things I was showing you on the chip earlier. The 6510 microprocessor, the brain of your 64, has 16 legs. With these legs, total number of address lines, it can address 2 to the power of 16, or as we talked about, 65,535 memory cells, 64K as we learned much earlier in the first video, of course. Each of these cells contain 8 bits or 1 byte. Once the 6510 has addressed a memory cell with its 16 legs, the address lines, it then uses 8 other legs, the data lines, to either read or store 8 bits of data from or to that memory cell. In machine language, mnemonics are always 3 characters. LDA is one such mnemonic. However, it is important to practice with machine language and use a guide such as the Commodore 64 Programmer's Reference Guide as a mirror in order to get used to the instructions, what the instructions look like and how many parameters they contain. And I'm always citing the references as Peaks and Pokes. Machine language is also known as assembly language. Any surprise to that? The book introducing Commodore 64 machine code describes it as a set of abbreviated commands, words called mnemonics we discussed, which are to be discussed soon. The numbers which are the data or address numbers. And here's the definition for mnemonic. This is a word that describes a machine language instruction. Wikipedia describes it as a memory device to learning a technique that aids information retention. Not sure, I just threw that in there, I guess. It is essentially an abbreviation of an instruction as mentioned above. For example, the statement LDA reads load the accumulator. So what you're looking at when you're seeing machine language instructions are abbreviated commands to kind of make it easier just to type in that little subset instead of having to come up with a larger thing like typing out load the accumulator every time you want to load the accumulator. So we're going to study about cycles next, which are a real interesting read, by the way. The number of cycles will be very important as you enhance your programming knowledge and skills in machine language. This will determine how long instructions take to complete, which is especially handy when you are writing IRQ or any type of interrupts, also known as rasters. This is also referred to as timing, which is managed by the internal CPU clock. In the book, Machine Language for the Commodore 64 and Other Commodore Computers, Butterfield states that most instructions run at the fastest imaginable speed. He says to count the memory cycles since that's how fast the instruction will execute. When we begin writing code, you will see the Excel charts columns for num of cycles. That'll probably be in the 3rd or who knows, 4th video. This was extracted from the Programmer's Reference Guide. This chart is a good way to see how many cycles a particular instruction takes. Also, according to the book, Commodore 64 Programmer's Reference Guide, I'm going to do a little correction here. Machine language instructions either change the contents of a memory location, as mentioned earlier, or change one of the internal registers, special storage locations inside the microprocessor. The internal registers form the very basis of machine language. Other uses of an index register include temporary storage counter and memory load store. And then I cite the references. I'm not going to read the references, just to let you know I'm citing them because I don't want to feel like I'm plagiarizing, although I am plagiarizing at this moment. So excuse me on that, but it's all technology. And I didn't have time to sit there and rewrite everything in my own words. I'm not going to sit there and try to sell you a book or anything, but it is what it is, right? So timers. Inside your Commodore 64 are many timers that are counting up and down. Jim Butterfield states that even when you have a machine language program running, the computer freezes 60 times a second. Got some little typos in here. The computer undertakes a special activity called interrupt processing. It stops whatever it was doing and switches to a new set of programs to do several tasks. Flashing the cursor, I'm going to enlarge this a little bit here, checking the keyboard, and keeping the clock up to date and checking to see whether the cassette motor needs power. When it's finished, it unfreezes the main program and lets it continue where it left off. The interrupt might take place between a compare instruction and branch instruction. Hundreds of instructions might be executed between such statements, yet nothing is hard. The two instructions work perfectly together to achieve the desired effect. The compare instructions, CMP, which is to compare, CPX, compare the X register, CPY, compare the Y register, test and turn on a special flag on or off, resulting in an equal or not equal. This determines the route of branching, to be discussed much later when we get into the instructions, of course. This is possible with the wonder of flags, which we're going to be discussing next. And there's the references being cited again. Registers and flags. Before we begin discussing and writing code, it is necessary to have a good handle on the purpose of registers and flags. These may appear perplexing at first glance, but as you begin to enhance your understanding of machine language and write in assembly language, you eventually start to grasp their primary significance. Below is a Vice screenshot of all the registers and flags for the Commodore 64. You can view this by clicking on the File menu and selecting Monitor, or use the shortcut keys Alt+M. And here's the definition of Vice, since we'd already talked about the monitor, and here's a screenshot of Vice below if you guys have never seen it. So Vice stands for the Versatile Commodore Emulator. It's a program that can emulate a Commodore computer system environment as essential to owning the actual computer. Here's a screenshot of that tool. It can be embedded into your favorite compiler and executed in real time. And you've seen videos of me doing this already when we're doing a machine language project. We have it already embedded inside, so it executes when we do a regular compile. However, I am unable to get to this function properly, so we will be using the register panel in CBM-PRG Studio instead. So I've been playing with Vice a lot, and what I'm stating here is I couldn't get this register to read right when I try to change the zero, set the zero flag, or if I try to, set XY registers, stack, whatever. It wasn't throwing values in there, and I didn't really have time to play with it and figure out why yet. So here's the definition of CBM-PRG Studio. It's Commodore Business Machine. It is a tool that is used to write in both BASIC and assembly language, possibly other languages too, I don't know yet. Here's a screenshot for reference. Note, this is not a tutorial for this tool. Please use your favorite search engine for further information. Now I do have a Vice tutorial on my channel if you want to see that. This tool is used to assemble programs into machine language using the built-in compiler. And here's a screenshot I have of actually a scroll demo inside of Vice here. I'm sorry, inside of CBM-PRG Studio. Vice runs out of here, so when you execute this debugger, we'll learn and see that in later videos. You'll see that little blue screen pop up and it executes your code. And probably erase this. This was an old note. Before we go into a very detailed explanation, I thought it would be important for you to learn which instructions are managed by the flags. You can also use this for further reference as you begin your journey into the amazing world of assembly language, or machine language as it's sometimes known as. About that, assembly language is because it's actually the words and the instructions that's kind of assembled into machine language. Machine language is actually the binary code, so it's kind of a toss-up what people like to call it. I use the old term machine language for myself. Information is extracted from the book Commodore 64 Assembly Language Programming. Now here we're going to study these flags, and just kind of a testimony up front. I didn't know much about these flags going in, and a lot of my examples you've never seen me use these flags. Now going forward, more likely I'll be able to use them now that I understand it. And it was this journey into really researching these books and putting together this material that really opened my eyes to something I've never seen before, which is wonderful because I've seen how easily you can go in and you can watch what the flags are doing and why they're important. So I found some information. I'm going to go ahead and continue on with that, about that. So N is the negative flag. You saw that earlier Vice screenshot. I'll just pull this over for a second. We'll look at this in a minute here, but I wanted to show you. Get this over here a little bit. These are the status flags here at the top you see right here, and this is what I'm talking about. These are the registers over here, of course, right here, the accumulator, X, Y, and the stack. But over here, or this might be the stack, I'm sorry. Right here is the registers we're focusing on right now, the flags. So I'm going to leave that up there just so you can kind of see that. So negative flag, or the N, you see that right here, it's actually a bit 7, it's right here, a little N there. So this set is set when an arithmetic operation results in a negative result. The flag is controlled by the instructions ADC, add with carry, and ASL, bit, compare, compare y, compare x, decrement, decrement x, decrement y, exclusive or, increment, increment x, increment y, load the accumulator x, load the accumulator y, left shift right, or the accumulator, pull the accumulator, process. I'm getting stuck here. So PLP, rotate left, rotate right, transfer x to the accumulator, transfer accumulator to x, transfer accumulator to y, transfer x to the accumulator, transfer y to accumulator. I wanted to read them out so you can understand. Those are the abbreviations, and those are the actual words of how you would actually say them if you read them. So it is set when the result byte of an operation has its high bit set, which we looked at here. Currently it's highlighted over here on the left here, showing a negative number in 2's complement representation, because the n keeps track of the negatives that are going through the accumulator essentially. To check if a statement such as LDA number hexadecimal 65 sets the n flag, just convert the hexadecimal number to binary and look at the flags. If the n flag is set on, the branch minus instruction will set. Otherwise, it's ignored. Little typo here. If the n flag is off, the branch plus will branch. Okay, so I'm going to show you real quickly. I'm just going to put that number here on the screen, 65 here. And I'm going to show you, just pulling this up here for a second to show you. There's the 65 using the calculator Microsoft, and you just click binary here, and you can see that the 7th bit, I think that's 0, 1, 2, 3, 4, 5, 6, 7. 0, 1, 2, 3, or it's 1, 2, 3, 4, 5, 6, 7. So the bit is set right here. It's the one that's actually set. Maybe I read that wrong, but anyways, that's how you convert them over or whatever. So V, which is the next one in line here, is called the overflow flag. This is set when an arithmetic operation results in an overflow from bit 6 to 7. So bit 6 from 7 right here is bit 6 where we're at, and it can overflow from here and it can carry on into the next one. And it tells that the result will be wrong unless overflow allowed for. The flag is controlled by the instruction add with carry, bit CLV, clear the overflow flag, PLP, return from interrupt, and subtract with carry. Set. So this is talking the rest about the V overflow. Set when an operation results in a carry from bit 6 into 7. Oh, actually this is a repeat. I just need to erase this then. So it signals the condition of bit 6 at a memory location being tested and works with the bit instruction for further information here. If the V flag is set to on, the BVS will branch. Otherwise it is ignored. If it is off, the BVC instruction will branch. It can be reset by the CLV, which is a clear overflow flag instruction. However, there's no instruction to set the flag. Now, the definition of 2's complement, according to the machine language book of the Commodore 64, it states that all numbers having bit 7 are considered to be negative. Okay, I think I've got a repeat on. Oh no, these are the rest of them. Okay, so I just had the definition in the center there, so we wouldn't lose track of where the definition came from. So continuing on with the next one here. Now this one right here, 765, is ignored, so we go right on to 4, which is number for B for break. So the break flag is set when a program interrupt is brought about by the BR key instruction. The next one is the decimal flag. We can see right here, the D. And I don't think I have a way to zoom this or I would have shown you, but that's essentially all I got right there. So the D flag is set when the arithmetic operations are to be carried out in decimal. The flag is controlled by the instructions clear decimal, which is CLD, PLP, process something. I gotta look that one up. I don't use it, it's very uncommon register. Return from interrupt and set the decimal flag. And then this says set to let processor operate in decimal or BCD, binary coded decimal mode, not binary mode. So it's also being used when you want to convert from binary to decimal. The next one is interrupt. We can see that the next flag down here on the line. It's called the interrupt flag, of course. So it's set when an interrupt sequence is an operation. The flag is controlled by the instructions BRK, break, CLI, clear the interrupt, PLP, RTI, and SEI. And it says set to disable any interrupt from a hardware interrupt request. So I was cheating here. I was looking up what this PLP instruction is because I couldn't think of what it is. And it says pull processor flags there, according to Google. So pull processor flags. So Z, this is a really important one. This is used a lot. The 0 flag, which is the next one right down here. I'll highlight it right here. You can see it. And it's, we say we got 5, 4, 3, 2, it's bit 1. So the 0 flag is set when an arithmetic operation results in a 0 answer. The flag is controlled by the instructions ADC, which is add with carry, and accumulator shift left, bit, compare Y, compare X, decrement X, decrement Y, exclusive OR, increment X, increment Y, load accumulator X, load accumulator Y, left shift right to accumulator, or the accumulator, pull processor. I'm not going to remember this. It's pull processor flags. It doesn't look like that when you look at PLP, but it's actually, I think if you could think of a yell in front of it, a U right here maybe, like this. Might be an easier way to look at it, pull processor flag. So rotate left, rotate right, return from interrupt, subtract with carry, transfer accumulator to X, transfer X to the accumulator, transfer Y to accumulator. And this one is set when an operation results in a 0 byte or equality in a comparison. It is checked after a compare statement, and the branch determines that the flag is on, which is equal to 0, or if it's off, which is greater. Actually, I put greater or less than 0. I should say greater than 0, excuse me. Is not equal to 0. So C is a carry flag, another common one used when you do addition in, various machine language instructions, like load accumulator. This one indicates the presence of a carry or a borrow used during arithmetic operations. Also set during shift and rotate operations, that's the ROL and ROR, we'll be covering much later. When you want to shift and keep track of the bits in the accumulator to move from an 8-bit to a 16-bit and carry over. It's also known in math as the carry in the 1, so to speak. Or the, what do they call that, where you have to carry the remainder. I think that's it. Okay, so return, interrupt, subtract, and subtract with carry. I don't know why I had this in here twice. I probably lost an instruction here somewhere. Okay, so I'm just going to make a little note here for myself, so I knew that I might need to come back and check that. Okay, so this carry flag is set when an operation results in a carry, no borrow, and an addition subtraction. It also serves as a 9th-bit extension of the accumulator in a shift rotate operation. And this is once you've actually carried over from 255 and you want to add that additional 1 on, it's going to set the 9th bit, so to speak. So it's essentially, I guess you could say it's an invisible bit, but it's necessary for it to do the calculations. It is sometimes used as a user flag because it is easily programmable and does not have any effect on most operations. After a compare, the C flag is set to on if the register X, Y, or accumulator for A is greater than or equal to the value compared. And there's our cited reference there again. Okay, so listed below is a screenshot I found from Wikipedia that provides a little bit more information in case you are still confused. Each letter corresponds to the 8 flags we've gone over, which is negative, overflow, break, decimal, interrupt, 0 flag, and carry flag. So right down here you can see them. This is a kind of chart if you want to look at it. I'm not going to read it, but it just shows you some more information about what they do. Now we're on to the status register. The status register, this is not an instruction, and the status registers, well actually I think it's all these if I'm not mistaken. Correct me if I'm wrong on that, but okay. Rather is an 8-bit register like the accumulator, X and Y register. It can also be referred to as the processor status register, or can be found by its one letter, P. I don't see a P in CBMP Visual Studio, so not sure where they got that from. This was in a book. The SR performs as if it contained 8 individual bits, which are used as signals or flags. The Commodore 64 only handles one status flag at a time. It will either set the bit to value 0 or 1, or test in the status flag to see if it is set to 1 or cleared with a 0. The 0 flag is one such flag that works with arithmetic processes. So whenever the result of a calculation is 0 in the appropriate register, A, X, or Y, the Z flag is set to 1. However, if the result of a calculation is not 0, the Z flag is set to 0. The book introducing Commodore 64 machine code refers to it also as a flag register. It is used sort of as an electronic notepad. 7 of the bits in the register, 8 altogether, are used to record what happened at the previous step of the program. If the previous step was a subtraction that left the A register storing 0, then one of the bits in the status register will go from 0 to 1 to bring this to the attention of the MPC, which we learned about as the CPU, or that 6510 chip. If you add a number to the number in an accumulator and the result consists of 9 bits instead of 8, then another of the bits in the status register is set. Each bit is then used to keep track of what just happened. You can make branch commands depending on whether the status bit is set or reset. Branch commands will be covered extensively later. Just know that if a branch command, which is branch equal, as one command to show you an example before we look at the instructions, is out of range, CBMP or GStudio or your favorite compiler will complain and throw an error. So if you're trying to send it beyond a certain range, which we'll learn about later, there's 128, negative 127, it'll throw this compiler error because you've already tried to branch too far forward and back. This will usually prevent your program from being run since an error still exists. So reference material, there we got our citation. This is just showing an example for this program below. I don't know if I can get it all on the screen here. So further elaboration taken from Introducing Commodore 64 Machine Code. So I left this in here so you can see. The above table, which is right here, shows how the bits of the status register of the 6502 are arranged. And we saw that over here, of course, earlier. Now remember, these numbers down below here are telling whether the flags are on or off. And in this example, since the program's not being run, I could run this just to show you because I have one running here real time. Oh, actually, I got to compile it again. I'm not going to show you the program since we haven't gone into the code yet, so I'm just going to sneak this over here for a second, but I could still run it privately on this side just to show you. And when I click this little button here, which we'll learn about later, you'll see the flags changing as it executes and goes through the code. The Z flag will be set once right there, once it hits the register, and it'll reset as it hits the next register to clear it again. So that's kind of how you can see it in real time and why I discovered that the status registers are very important to watch, because you need to know what the Z flag's doing, carry flag's doing, you know, all that stuff, negative flag and such not. Interrupts when you get in rasters, of course. It's interesting to watch it too. It also shows you the cycles. We talked about cycles earlier. It shows that we're 7 cycles. Total cycles executed was 70, but I need to reset this because it accumulates them, so I'm just going to run it again. And then you can see this up here. This is the number added, just showing you as it basically adds the number, it kind of is calculating here, so to speak here. So what we're going to do is read this, okay, down here. Okay, I wanted to show you this is executed. It's 7 cycles. Okay, we'll come back here again. So the above table shows how bits of the status register 6502 are arranged. Of these bits, 0, 1, and 7 are the ones that are most likely to use at the start of a machine code career. And 0 being a negative flag, or sorry, 0 is the carry flag, 1 is the 0 flag, and 7 is a negative flag. And remember, I'm referring to these right here. When I'm saying negative, I'm looking at these values right here we talked about earlier. The above table shows how to, okay, I read up about that, excuse me. The use of the others is rather more specialized than we need at the moment. Bit 0 is the carry bit or carry flag. This is set to 1, which we talked about, if a piece of addition has resulted in a carry from the most significant bit of a register. I don't think in this example I have one to show you, but later we'll watch it and we'll learn about the carry flag, which is used whenever you're adding with that carry value. But that's to be covered later. This is set to 1 if a piece of addition has resulted in a carry from the most significant bit of a register, or basically going beyond 255. If there is no carry, the bit remains reset. When a subtraction is being carried out, or in a similar operation like comparison, then this bit will be used to indicate if a borrow has been needed. It can, for some purposes, be used as a 9th bit for the accumulator, particularly for shift and rotate operations in which the bits in a byte are all shifted by one place. And here's a screenshot below to show you. you can see it's showing this is the low significant. The most significant is always the furthest bit away. And then that's how you know. This is basically going to keep track of this as it's calculating. It's going through these. Let's say if we do like in my example, we had an ASL here, accumulator shift left. If I could just quickly pull this up here for you. I'm just going to have to, I don't know how to get to the register without setting it, but it's right here and C00 right here. So you can see the ASLs right in here. These are accumulator shift left. We'll learn about those later, but those are basically calculations or multiplication. So it's multiplying. As it's multiplying each time, you can see here, it's multiplying through. The rotate, basically, we'll learn about that later, is keeping track of the carry bit, so we don't lose it when we go beyond 255. And it's basically calculating until you get too high to 255, and then it finally carries that bit over, and then you would want to save it in a higher, most significant bit. So I know that won't make sense until we get into code, but some of those who are kind of skilled will understand what I'm talking about. This book is examples taken from, I think, Jim Butterfield's book. The 0 flag is bit 1. Remember, that's this bit right here. It is set if the result of the previous operation was exactly 0, but will be reset 0 otherwise. It's a useful way of detecting equality of 2 bytes. Subtract one from the other, and if the 0 flag is set, then the two are equal. The negative flag, bit 7, that one way over here, is set if the number resulting in a register after an operation has its most significant bit equal to 1. This is one type of number that might be a negative number if we are working with signed numbers. The bit is therefore used extensively when we are working with signed numbers. And signed numbers is a whole new ballgame, but we'll talk about that when we visit that part later. You can alter some of the bits of the status register selectively, advanced level. I believe it's from a hardware level if I'm not mistaken. For the most part, we don't load anything into this register or store its content. It is used almost exclusively as a way of keeping track of what has been done. So that's a lot to go on the 0 flag, but the 0 flag does cover a lot. It is affected by what various opcodes do within a program. So I think we're getting pretty close. We got 32 minutes in, so I'm going to keep going forward here. I'm trying to get this into a section before we get down to here, the index registers. I don't know if I'm going to make it, but I'm going to try within 45 minutes. Okay, so here's the citation. You can see the Z flag here is showing if it's not equal to 0, it's going to be set to 0 there. If its result is set, then it's going to be equal to 1. That means it's set to 0, and the condition shows it's true, so it's 0, otherwise it's false. And this is what I showed you here already. So it's a diagram of what we use in the CBM P Studio. So I took it up here earlier to show you. And then we can leave this up here to show you. By observing the flags above in the top window, which I think is the same one I got right here. Actually, it's a little bit different, it looks like. Within CBM P Studio Debugger, you can clearly see that the 0 flag is set bit 1 right there. And you can see it right there, of course. Actually, that's the interrupt flag. 0 is right here, excuse me. It's set to 1. You can ignore bit 5 as it's not used. That's this one in the center with the minus sign. As far as I know, it's not used anywhere that I've heard of yet. So, right there. Also notice that the XR register, which is our X register, shows a 07 and the wire shows 32. So I put in that 7 and 32. As we start to work with code, you will begin to understand why these registers contain such values. That's when we're going to learn about loading values into X and Y and so forth. But I just do it here as an example to test it while I was learning it today. So now about the monitor registers. The SR, the AC, the XR, and YR are all 8 bits, 1 byte in size. As we learned very early, the AC or A depicted by AC in the CBM PRG Studio Debugger screenshot, AC right here, accumulator, it's known as the accumulator. It is the busiest place in the computer. Logical instructions such as exclusive OR and AND drop their results here. Most of the bytes streaming through the computer come through the accumulator. Nearly everything that occurs here will have an effect on the status register, which is the SR right here. I couldn't think of what it was now. It says it's status register. Okay, we learned earlier that a byte ranges from 0 to 255. This was in the first video. I thought it would be important to append a note here mention that these bytes, according to CBM PRG Studio or any C64 compiler, may be instruction codes such as LDA, store, etc., which allow a task to be performed. As you will learn soon, these bytes are evaluated by your computer in sections, and we'll see that down here. When the MPU, the processor, reads an instruction byte, it analyzes it to see if it is followed by other instruction bytes. For example, an instruction to load the accumulator looks like A9 hexadecimal 01 169,1. Others may be data bytes, which are numbers to add, store, or shift. They can also be ASCII characters to produce text on the screen. You will learn about this when we cover loops. And I show an example here. As you can see down here, you see the A9 169 is the decimal value, and you can see the 1 being loaded in here. I know we haven't covered it yet, but you see the 1 there. This is how the compiler is seeing this information. And then we see the mnemonic right here for load the accumulator, and we can see that the A9 represents the load, and then the 1 represents the 1, of course. And that's just what the screenshot, it's known as assembling a program. Let's skip that part. So the X and Y registers are similar since they assist the accumulator. They are used as addressing indexes to be discussed below. As an example is load the accumulator with hex 4000, X. This instruction, when used with an LDX command, can cycle through memory locations as a counter is increased, decrement X, which we'll learn about, or decreased, decrement Y. Finally, they must be repeated just like a for next basic loop to reach the next available address. And the definition here is of an address, also known as the address number. It's the electrical signals that correspond to the zeros and ones. They appear as a set of connections called the address bus, which link the MPU to all the memory, RAM, and ROM. In the compute book, Machine Language for Beginners, addressing is described like this. If you could peer down in the heart of your computer, you would see these numbers being received or delivered and received all over the place in memory locations. Sometimes the numbers arrive and are sent out unchanged to some other address. Other times they're compared, added, or otherwise modified before being sent back to RAM or to a peripheral. And these are common whenever you want to look at like a hex loader, what do you call it, hex display. You can kind of see all the numbers. If you scan through memory and do a memory loop, you can see it that way. Maybe we'll do that much later. The stack keeps track of numbers such as those pulled from an RTS or returned from subroutine instruction. These subroutine addresses are managed together in a list called the stack. The stack, I believe this one, if I'm not mistaken. We have some values in the stack here registered. These are the stack values, by the way. Actually, we got a lot in there, looks like right now. Interesting. Okay, the computer will automatically handle the stack pointer for us. All we have to do is push a number onto the stack, which is this values down here. Basically, it pushes and it starts at the bottom. We'll learn about that. The most important thing is to always follow a push, a PHA, push the accumulator, or a pull the accumulator, PLA, or the computer could send your program to no man's land, which results in a crash, often losing your work. Also, it is important to know that the stack is organized backward in memory, as I talked about, starts at the bottom here. It ranges from 0-100, we can see the 0-100 here, to 0-1FF, and you'll see the 0-1FF here. Hopefully you can see that. Right there, just to show you, I'm looking at 0-1FF, and you see it starts at 0-100 there. So the first position in the stack is as 0-1FF, and the last is as 0-100. I just talked about that. So in the book, Peaks and Pokes for the Commodore, a basket software describes it as a temporary storage area in memory. The author from the book, including Commodore 64 machine code, states that the contents of the registers of the 6502, or 6510, whatever, are placed into a part of the RAM memory, which is called the stack. This, incidentally, is a good reason for being careful as to where you place your machine code in the memory. If you wipe out the stack, the C64 will not like it. The stack is located in the range of memory between addresses. These are translated as 256 to 511. Remember, it starts at 511 first when you throw it on the stack. When the RTS instruction is encountered at the end of your machine code, the bytes that have been stored in the stack are replaced into their registers and normal action resumes. If you call a machine language program into action by any other method, not using sys as in BASIC, you may have to attend to the salvage operation for yourself as part of your machine code program. This includes using push and pull commands, PHA, PLA. Jim Butterfield describes a stack like a stack of documents that you may drop or push onto the stack when you take an item back again or pull, you'll get the last one that you put there. Formally, it's called a last in, first out LFI discipline. It's natural and easy to understand. He also mentions that if you push 3 items onto the stack, be sure you pull those 3 items off back again. Don't ever branch away and leave the stack littered. And a great friend of mine in a Google Hangout, Siggy, also said you can imagine it as a deck of cards, which I thought was awesome. When you take a card off the bottom of the pile, the stack, then you just don't want to toss the card away, but rather return it to the card deck later so the computer doesn't crash. So excuse me for making this video go over a little bit. I'm trying to do 45, I'm already at 40. I wanted to show you a deck of cards here. If you can imagine a deck of cards, where am I at here? You can see this could be represented as a stack. Of course, you couldn't put this many in it. You would basically, when you add an item to the stack, you would be taking this bottom one off like this, and then essentially you just don't want to leave it like that. If you do, it'll crash. You want to make sure you put it back onto the stack, and it kind of just go in that order. If I'm not mistaken, if I don't have that backward. That's just kind of an illustration for you. The stack is actually quite common when using interrupts, which will be covered later. I won't go into detail here in order to keep the tutorial as consistent as I can. You could actually push 1,000 items onto the stack. The stack would never leave page 1 as the stack point went down beyond 0. It would wrap around to FF, because remember it starts at 0, 100 or 511. So if you keep going beyond 256, 255, 254, it's going to start hitting memory locations that are already used, and it's going to crash essentially. However, you would never get those 1,000 distinct items back, of course. Time for another screenshot from Jim Butterfield's book so you can see this up close and personal. So here's another example of the stack in case you didn't get what I showed you and what I showed you earlier. So basically it takes an F8, puts it on the bottom of the pile here, and then once you take it and put it back off here, and it's like these stack of cards or stack of plates. You think of the stack of plates the same way, and basically they're shifting. I guess you could say shifting down. As you can put more. You can put more than one item on the stack. So as you keep filling them, these are basically, it says free here. You'll see used will become. I'm sorry, this is free. This will become used, and these are all used currently, but these would start as free essentially. Okay, so earlier we saw a screenshot in Vice of the stack. I'm showing it again here for further clarity so you can see how the computer manages the stack. This is an example of the process status register, hence the one-word register for abbreviation, which we saw this earlier, but I'm using the CBR PRG Studio since I can't get Vice to work right. So currently it is pointing the stack at hex address F6, which is decimal 246. Knowing how this processor status register works is the key to advancing the machine language as I am learning. The SR, AC, XR, and YR are 8 bits in size. I think I might have mentioned that earlier. Excuse me, these are pulled from several references. Didn't have time to check that. They are not located in memory proper. You can't peek them since they have no address like the rest of memory. They are zones of the CPU. So you can't look at them. They're just used basically for the computer to keep track of what's going on with processes. So a definition of a pointer here, since we talked about that, is looking at the 2 bytes side by side in memory, add them together, these are the high and the low bytes, and multiply them by 256 to get the base address. An example would be 0 plus 4 times 256 equals 1024. That's screen memory for the Commodore start address. The 0 is one pointer and the 4 is the other pointer, so 0 is the low and 4 is the high. Just know that the pointer always consists of 2 bytes, 0 and 4 as in our example. The first is known as the LSB, as I mentioned, the low, that's the lowest significant byte, and the second number is the high, as I mentioned, the most significant byte, or MSB. The computer also utilizes a CLC before any addition. Also, if adding a 4 to the LSB results in a carry, we want to be sure that the MSB goes up by 1 during the add with carry. We will see examples of this when we start writing some code. And here's a citation for the references. So I can pretty much stop here because these are going to go right into the instructions. And I think this is perfect where we left off. The instructions down here, what I was talking about earlier is we'll talk about this next time since we're over in this video. We'll learn about the cycles. As you saw me earlier when I executed this, it shows 7 cycles. So it shows what each instruction is doing. So when it hit this LD8 here, it was basically executing so many instructions here. So this program is actually pretty fast if it got through 7, I'd say. I'm not sure if that's actually accurate, but anyways, it shows you what they all do in the instruction. Instructions can be can accumulate in the middle of a loop and stuff like that. I think we might have talked about that much earlier, or actually that's probably later in the code. I've been doing so much writing here, so I'm probably not sure what I've covered already and what I'm yet to cover. I mean, this document is very extensive. You can see I don't have all the instructions in here, but just to kind of give you a sneak peek ahead here, you can see I've been doing my homework. We'll talk about the addressing, and there's a lot more to come here. So stick with this, because it's going to get really good. We'll learn about calculations, how binary numbers are calculated, and I basically repeated some stuff here. So a lot more to go. It's already 46 pages, and we're kind of over it. Hey, we hit 45 minutes. Awesome. Well, wow, that was a lot to go over. A lot of reading, but hopefully you understand the stuff we kind of reviewed here, and the examples I showed you will make a little bit more sense. When we actually start coding, they're going to make much more sense. Right now, they might still be floating around. You might be like, okay, I saw all these registers, I saw these flags, now what? Now that's when we're going to get into code. Next video, it's getting good now. We're going to finally start evaluating these using the status registers, and we're going to be able to check the flags and stuff like that and see what's really going on, and start, you know, working with some real examples, and finally get CBM PRJ Studio to show us some results. But like I said, there was still a lot to cover. Essentially, I was going to make this even more extensive because I found a lot more stuff to kind of give you an overview here. These alone are just some of the stuff I've been writing down, and if you can see, these show the page numbers and everything. I'm just kind of giving you an idea of what I've been doing here. I wrote down all the page numbers. These are the page numbers over here on the side, and you can see these are what I've been discovering and writing down as I've been researching it, and just, you know, just keeps going on and on and on for each of the books. And then this one goes on the back. This one was probably the longest one I ever did, and it was this book right here, which is Assembly Language for the Commodore 64, which I found out was a university book. It's really it's written at a level that people can kind of pick up on, because the chapters are super short, but there's really good information there. But that's it for this video, guys. Please always like, favorite, subscribe to this channel. I hope you enjoyed this. Also, to come forward, Machine Language Project. We're still working on that right now. We've got a great team. I'm meeting newer people. You are definitely welcome to contact me if you want to join. Let me know. I'd like to know what kind of skills you have. If you want to just sit there and watch, that's totally okay too with me. I'm totally fine. So just send me a message. Get added to my Facebook there. I'll put the link in. I probably may have not included it inside of the descriptions, but I'll probably try to put it in this one just to be sure. And also, you saw the capture card that I've been working with. I've got a lot of disks that I want to start showing. So we got basically 3 different things going on here. We got the Machine Language Project. That's kind of getting some help with that. We've also got this instruction, which I think goes hand in hand with the Machine Language Project, this tutorial. And also the videos for the people who want to watch, you know, the games and just see some fun stuff. And I might just do some talking over the videos and stuff like that once I learn how to embed a mic inside of the game capture with all that stuff. But anyways, thanks for guys for watching. You guys rock, and have a happy Easter. Thank you.